Welcome everybody, and thanks for joining our first technical webinar from Herios Next Sensors. For those who don't know me yet, my name is Lisa Würke. I'm responsible for the marketing and communication activities at Next Sensors and will support Martin today in regard to your questions. So today we have prepared several slides to strengthen your technical knowledge base and to improve the customer consultancy in order to technical questions. Our speaker, Martin Bleifus from Application Engineering team, will guide you through the presentation and is open for questions which will come up today. So on this slide here, I will give you upfront a few information. So the webinar is planned to have a duration of 1 hour, which includes a Q&A session afterwards. The participants are international distributors and internal colleagues from Herios Next Sensors. The session today, please note, will be recorded and used afterwards for internal trainings at Herios Next Sensors. Regarding the settings in general, all attendees are muted by default. But if you have any questions during the presentation, please address them in the chat box, which you can see on the right side. Or you can sign a hand and I will come back to you to these questions. So when you have used the chat box, I will forward this question to Martin. And if you have used the hand signal, the hand sign, I will unmute you and you will be able to ask your question directly to Martin. Please make sure that your audio works. Our recommendation is using the headset. And another option will be to dial in via phone if this is not the case. So before we will start now, and I hand over to Martin, we want to start with a short survey to query your current knowledge base regarding PT temperature sensors. And now you should see in your presentation a short survey. Please answer in regard to your knowledge base to start our technical training.
Lisa, currently I can't see the feedback. Please give me a sign if we are ready with that survey, please.
Yeah, a few are still voting. Okay. This is the result. And thanks for participating in this. And now I will hand over to Martin, starting the technical webinar.
Yeah. Thanks also from my side for joining that first Next Sensors webinar. I'm the head of the application engineering, and I started at Herios in 2005, only as a small explanation to my person. And I'm with Next Sensors for roughly 4 years. And to support a more stable signal here, I will switch off directly now my camera. Okay, nevertheless, you should be able to see the presentation, and the plan now is to show you the agenda and the topics for the 2 days training. First of all, we want to clarify what is a sensor. And the second thing is we want to compare the different resistance technologies. In the third point, we describe the influences to the resistance and in the end to the accuracy of a sensor. Then we want to talk about tolerances and ranges. And then I want to show you different sensor types and differences between a wired sensor and a sensor with the SMD type, what means surface mount device. And in the end, more or less, I want to show you some samples for installations or how you can pack our sensor for best use. Coming to that introduction, what is a sensor? A sensor is a device whose purpose is to detect changes in the environment. That means anything else should be not sensed. Yeah? The sensor or a good sensor is sensitive to the measured property, clear? Is insensitive to any other properties. That means the external influence to that sensor should be avoided or reduced, that the sensor is detecting what you try to measure. And a good sensor is also not influencing the measured properties. What means if you have a sensor in a gas chromatograph, for example, then this sensor should not outgas and therefore influence the result of that gas chromatographic analysis in the end. These are some examples for sensor types, but we hear a bit more detail about the different types later. The active principle of a resistive sensor is that depending on the measured quantity, the ohmic resistance of the sensor will change. The most important and simply spoken idea of our sensor system is with higher temperature, the resistance of the sensor is increasing. And for sure, if the temperature goes down, also the resistance go down. And this is very important, especially if you compare or if you can see other resistance sensor types like an NTC, KTY, or a PT. PT is our sensor type. It's a positive temperature coefficient, and we use a platinum technology as resistance. The NTC, and this is really what the character describes, is a negative temperature coefficient. That means the higher the temperature, the lower the ohmic value. And the KTY is also a positive temperature coefficient type, but it's a complete different method how you can how the system works. Here you see in a small explanation these three types, which uses the resistance for measuring temperatures, and our favorite for sure is currently the platinum temperature sensor. In that overview, we try to compare a bit these three sensor types. And what you can easily see in the first line is that our sensor is standardized. It's standardized in a DIN, in the DIN norm. And here is clearly scripted what the sensor should show you on which temperature. Our sensor is more or less a ceramic-based material, and on the top layer we have a metallization, in our case a platinum meander, and this meander is like a resistor. And yeah, our sensor is extremely accurate over a wide range, and it has a very, very good long-term stability. And this is the most important point, or one of the most important points, it's exchangeable because of that normation in the DIN. That means if you have trouble with a platinum temperature sensor, and it's described like a PT100, for example, and after 12 or 15 years, you will exchange, or you have to exchange that sensor because of some trouble, you can take another PT100 and put it in your system without any, regulations or something like that. That means you don't need to adjust your system. You can directly plug and play, use the new sensor. This is different if you work with an NTC sensor. The NTC sensors are not standardized. That means every supplier has his own curve which describes the behavior of the sensor under the different temperatures. Compared to our system, it's not a sandwich system. It's more or less a metal or ceramic metal composition. And this composition itself has a certain resistance, which leads to that resistance behavior of that element here. We speak about no high accuracy over a wide temperature range. You can see that in that curve here. You are in special areas. You have really a good resolution and also a good enough accuracy. But if it goes to the limits and away from that very steep area here, then the sensor loses the accuracy. And because of that ceramic metal composition, you have the problem over a long time that you create, or you can see some aging effects and some effects where the different materials interact under temperature and time, and this leads in the end to a different signal. And therefore the long time stability is not comparable to our sensor, because the ceramic base material, which is described here, interacts typically not with the platinum. If we have now as the third option a KDY, we have the same situation or the same description like in the NTC version. This KDY is also a not standardized characteristic. That means if you have to exchange your sensor after some years, it could happen that you don't get the same sensor again. That means you have to adjust your complete measurement chain. This is again a different design. It's a silicon-based material. It's also more or less a bulk material in the end, and this has also some problems over a long time because there are also aging effects in that silicon material. Because of that silicon, you have the next effect. You are limited in the temperature. It's around about 300 degrees, but it's a positive temperature coefficient. That means temperature is increasing and also the ohmic value. Let's have a closer look on the resistance and of the accuracy and what influences the resistance and the accuracy of a sensor.
Martin, there was a question.
Okay, sorry.
Yes. Do you believe there will be coming a norm for NTC sensors anytime soon?
I don't think so, to be honest. This is only my opinion, but the reason for that is with that bulk material, it's hard to describe it in that way that you can exchange it over the different suppliers, manufacturers, and so on. That means you have always some variances in the production, and typically if you purchase a very, very good NTC, for example, you get the curve and the characteristics with that delivery. That means the higher the accuracy, the more critical is to describe it in a good way. This is the reason why I don't believe that there is, at least in the near future, a kind of a normation for that NTC types. Yeah. Hopefully I could explain a bit my view on that thing. Okay, let's continue here. What influence is the highest? And we see here the meandration. This is a small line, which is more or less like a circuit. And this line has for sure the most influence of our sensor. That means if this line is much more longer, then the ohmic value will increase. And we see that later. It's a big difference in the design if you have a PT 100, means 100 ohm at 0 degree, or a PT 1000, which means 1000 ohm. Next influence is for sure also the wire. And the wires have typically a certain length, and our measurement point is 8 millimeters away from that edge. That means we have a very well-defined position where our measurement point is to define what the sensor, what the sensor's value is. But these cables or wires have for sure also small influence, and this influence could be also reduced by some special steps, and I explain that later. Here we can see that this line is not only a line, it's more or less really like a cubic circuit, more or less, which brings me to the next explanation. This meander structure is not a simple line. It's defined by a certain length, a certain height, and a certain width. And this is for sure then the description how we can calculate the resistance. This is a real picture. You can see really the meandration. We see some areas where we shoot out some circuits to trim our sensor to make it very accurate. And every sensor which comes from Heraeus is measured and trimmed. Let's describe a bit more that meander, because this is really essential, and this is more or less the core function of that sensor system. It's very simple. It's the ohmic law, and if I remember to my time in the university, my professor told me it's unbelievable what you can explain with the ohmic law, and it is. Here you can see the resistance. You can describe a specific resistance value of the material you use, which is in our situation, in the most cases, platinum. Then we have a profile, which is nothing else as a square meter or diameter of the structure here. And in the end, we have the length of that meandration, which is for sure also a big influence to the resistance itself. And here we have only as an overview some different materials for that specific resistance. That means platinum has a resistance of 1.06, and you see compared to gold, nickel, and so on, it's different. And you have to take care if you do a calculation, especially if you use different materials. Closer look to that meander shows, not only a line, as I told you before, it's more or less a cubic design a cubic shaped circuit and or a cuboid. And if you change this cuboid in dimensions, you can see that there is a difference. This is only an example. If you have a cuboid with a length of 1 meter, and here our specific resistance for the platinum, and with an area of 1.5 square meters, we can have a result of this ohmic resistance here. And if we do a change, that means we elongate our cuboid, yeah, then we get also a different result. Here we have 2 meters instead of 1 meters, and you see it's a double length. Result is double ohmic value. Same if we make a variance in the area, yeah, then it's also that we keep the length stable, yeah, double the area, and we get also a different ohmic value as result. For sure, if you have a bigger square, then you have a lower resistance. And in the end, if you take a different material, that means copper instead of platinum, then also the result is changing. That leads to a very, very simple explanation what the core technology is describing. Sorry, is there a question? Okay. That means the change of a geometry of that meandration here is really a very big factor of our ohmic value. That means the length and the width and the height and so on. That means the square. And a change of the material itself, the specific resistance, has also a big influence following that formula. This is the theory. Now we come to the practical situation. Only to get an impression about the size. You see that 1 euro cent, and you see directly besides the SMD part, it's an SMD 0805, and this has more or less a dimension of 1.4 and 2.3 millimeters. It's small, a small SMD part for sure. And here we have now a PT100, which describes the 100 ohm resistance. And you see these lines are small, but you can see it. In the second picture, we see a PT1000, and there's unfortunately a blue glass layer on top of that. And what you can try to see is that the lines are much more finer, yeah. And with the PT1000, you can see nothing because there is a top class which is not transparent. This is the reason why I made some X-rays. And here you see again the PT100. You see the meandration of PT1000, which is only a third of the dimension, more or less. That means we describe it as a line and gap description. And if you see the lines here compared to the PT100, we have only a third thickness or third part of the thickness of a PT100. And if we have now a look on the PT10,000, then you see that the lines are much more finer. Yeah, it's only 18% of the track line, and of the space is also only more or less 25% of a PT100 type. Yeah, and this is the reason why we always ask our customers if they try to get a PT10,000, for example, do you really need a PT10,000? Yeah, and it's very easy to say, hey, I need a PT10,000, because a lot of people or a lot of customers from us are used to work with NTCs, and 10,000 ohms is a very, very typical ohmic value for an NTC. But if you look on the structure here, you see and you can feel that it's much more harder to create a structure for PT 10,000 compared to PT 1000 or PT 100. This is the reason why it's not easy to do for us creating a PT 10,000, and we don't want to do that typically. But it's possible in general. You can see that. Very, very easy spoken. The higher the ohmic value, the finer the structure. Means the lines and the spaces between the structures of the meandration are more complicated to produce. And this leads me to the next overview, which is really, really only a rough overview. But if you have a low ohmic value with a PT 100, and you hire it up to PT 10,000, you need for sure as a measurement current a lower current also. And this is because of, if you speak about the measurement current, we have a meandration. This is nothing else as a resistance. And if you work with high currencies or with a high current, then the PT 10,000 is heating up faster compared to PT 100 because the resistance is higher. It's also following only the ohmic law. And you see also, if you look on the output signal, for sure PT 100 has 100 ohm, PT 10,000 has 10,000 ohm. That means signal output is for sure higher than influence of the wire length. If you have PT 100, the influence from the wire, from the cable in the end, is higher compared to PT 1000 because this is really an advantage of a high ohmic. Otherwise, there are not, or besides this influence, the other things are not really an advantage using a higher ohmic value. If we compare now the characteristics, that means the output signal between the PT 100 and PT 1000, for example, you see, again, the structure, it's much more finer and the output is also different. You can see here on the PT 1000, if you compare these both lines, that the PT 1000 is steeper line or shows a steeper line than the PT 100. And now a lot of people think, okay, it's clear PT 1000 is also more or automatically more accurate. And this is not the case. This is only a question of resolution in the end. And this is because of, we say here, this is the resistor and this is the temperature. If you do it in a different, or if you show this characteristic in a different way, like here, and we show here the change of the resistance in percentage compared or on the temperature line here, then you see both curves are more or less on the same level. And
another question, Martin. Sorry.
Yeah. No
does
problem.
This mean that the PT 1000 has a better response time than the PT 100?
No, the response time has more to do with how do you protect your element. Typically, you don't use it without any protection. And the second point is how do you contact the element, the sensor, to your measurement probe. And this is not so easy to say. You have to adjust your packaging. That means your housing to your applications. You can cover and protect your element very good, and it will survive over 100 years. but the response time and the signal is very poor because it's really covered. It's like a big coat you wear in the winter. Yeah, you are well protected, but yeah, you don't feel the changes in your environment. And this is more or less independent if it's a PT100 or PT1000. But if you use a longer cable on a PT100 compared to a PT1000, this is a different. We come to that point later, I think. Yeah. Hopefully, I could answer your question with that. And if not, you're invited in the end to have in our Q&A some chances to refresh the question. Yeah, this is what I said before. Typically, we measure our sensor from the edge at 8 millimeters away from the edge. That means this is our measurement point, and all of our sensors would be measured in that position. And if we have variances in that position, this leads, following our old ohmic law again and again, you see here we have 5 centimeter lengths, and this leads to a result of 2.65 per 10 minus 9, and we have that ohmic value as result. And now we said, okay, let's reduce and cut the wires down to 2 centimeters. Then the ohmic law tells us that the value of that shorter wire is now 1.06. But look at the dimension. Yeah, this is really not a big influence to our ohmic value. But this describes now a bit better. If you have 100 ohm and you have that different additional as an influence and compare it to 1000 ohm and you have the same ohmic value as additional more or less failure, then it's clear that the 1000 ohm is not so hard influenced by the length of the wire. We can see that later also with a different calculation. Why we have different wires is more or less described in that overview here. And we don't use different wires because we want to confuse our customers. It's more or less following the requirements of our customers. A lot of customers buy our sensor as an element, and they create the wire extension in their house. And then it's very hard for us, or it's very important for us to know with which technology they elongate the cables. Yeah, that means which technology they use for the wire extension. And if we use soft soldering, you typically need a different wire material if you use in the direct comparison hard soldering, because hard soldering withstands for sure higher temperature compared to soft soldering. If you jump then to laser welding, it's also good to have an optimized wire for that laser welding. That leads to the situation that laser welding is recommended to these types. And you find the wires we use in our brochure, in our internet site, and in all the technical descriptions. And we come to that later. I jump on our internet site to show you a bit what we try to show you there. And it's the same for resistance welding. Therefore you need also a special type of wire, ultrasonic welding and crimping. Crimping is a special connecting technology with a clamp. For example, you can press some materials together, and if you made the right choice with the pressed and crimped material, this could lead to a very, very good and strong interconnection, and it's not necessary to have, without that clamp, very, very special material. But you can do also a lot of failures. That means if you know what you do, it's really a fantastic interconnection technology. but you can do also a lot of failures. It's not so easy to judge in the end if the crimping is good or not. For our SMD types, we have for sure not a wired version. We use different interconnection technologies like wire bonding. This is a 300 micron aluminum wire from our colleagues at the HET business unit. And you see here it's ultrasonic bonding, and typically our wires here are with the thermosonic bonding connected to our sensors. That means different bonding, but one is ultrasonic and the other is thermosonic. But yeah, you don't, it's not important for you how we can connect our sensors. Important is if a customer is asking for a wire bondable sensor, then you could think about our SMD-SC, which means sinter chip. This leads me to the next point. This is the same sensor, but here you can see the top side like here, and flipped you see the backside. The backside is a metallized backside, and the metallization is a silver alloy, and this silver alloy allows us to sinter our sensor, or allows our customers to sinter the sensor directly on a DCB, a direct copper bonded surface, which could be a copper surface, or it could be also a copper surface with a gold layer on top. This sinter technology is getting more and more popular because of the use of new materials in power electronics, for example. We come to that point maybe in the next training where we speak a bit deeper about applications. And then we have for sure some applications for PCBs. And then you can use for the PCB solder technology, gluing technologies, and so on. We have for this situation a flip chip version and a normal SMD version. We see the different later. Coming to the wire connections. Here you see our sensor, which is a resistance sensor or resistant sensor. And here we see our wires, and then we put some cables on top of that. And if you connect cables, you have the same situation like before. These cables following also the ohmic law. That means with a long cable, you create a higher failure. And if you use two cables only, two wires only, then the failure is, given. You have to know that. You could, it's not a problem if you use typical wire lengths, smaller than, I don't know, half meter or so. But it gets more and more important if you have wire lengths 2 meters, 10 meters, which is really sometimes possible in the application. Then you have to take care about the wire lengths, and in the end of the failure, you create with that wire connection. But sometimes our customers need a 10-meter wire or a cable. Then you could use a 3-wire or 4-wire connection to eliminate this failure. That means it sounds easy to use 3 or 4 wires to eliminate that failure, but you have to think about, you need also 2 wires. You have to pay for 2 wires in general, but then you have to pay for 3 wires or even for 4 wires. And in the most applications, the cables are really special, and this is really a cost-effective factor in the end. And you have to take care if 2-wire connection is okay for you, if the accuracy is fine, or if a 3 or a 4-wire connection is really needed. Let's talk about tolerances and ranges. We have for sure different tolerances. These tolerances are typically described in the DIN B, DIN A, third part of B, DIN B, DIN A. This is more or less the limitation. And what you can easily see is the higher the temperature, also the tolerance is increasing. Yeah, that means the tolerance is not the same on each temperature. And you see this shape of a trumpet, we call it, and you have to take care about that. And this is only an ideal description here. In the next slide, you see more or less the real world. That means if you speak about third part of B here, then you typically get your sensor only for a temperature window of 0 up to 150 degrees. Yeah. If you speak about a tolerance DIN A, then the temperature is from -70 up to, or -50 up to 300. Yeah. And if you have special things like third part of B, yeah, it's like I spoke before here, up to 150. And if you have the full range, the description ends at 500 degrees. Sometimes customers ask for tolerance class A, for example, but they want work on a temperature at 400 degrees, for example. You see in that description that this is at least not described in the DIN. That means, you have to take care, and typically we can talk about what happened there. If you work in a range outside the description, it could lead to an aging process. It could lead to different other effects. And if a customer is going away from that table, I will call it, let's have a talk. If it comes to a discussion or explanation to customer, it's in my eyes always helpful to have that the chance to use our internet site. In that situation, we check if it works. In that situation, I click that link, and I want to show you what you typically find in that technical information, because there are a lot of basic informations, and please play with that website and look what we can offer here. That means we have a lot of assembly considerations. There are several factors and dimensions described. We have for sure also the reference tables here. You can download or print it out as a PDF for the PT100, PT200, PT500, and so on and so on. That means we have special tables here following the new DIN, the IEC standard 6751, and we have for sure also the suitable tables for the different ohmic values. That means also the tolerances which are included here. Here is also a description about the response time. Typically, it's highlighted on the data sheet, but as I tried to explain before, response time, the essential element is, or the essential parameter is how you code how you protect your sensor itself. We have for sure also the self-heating, what is meant with self-heating, and what's also really nice, please play with that. We have a FAQ. These are some slides, and you can jump over. If you think that there is something missing, please give us a feedback. We try to work on that more or less permanently. That means if we see that there are some questions highlighted permanently, we put it in the in the FAQs, and yeah, hopefully this is a living document for you and you can work with that. Yeah, this is the invitation. Please jump in our email, in our internet site, or to our internet site to get more informations. Now we can describe a bit more the different types we could offer. In general, the most share of our production are wired sensor elements, and for sure there is a high variability concerning the connection technology. I try to explain a bit why we use different wires. The other thing is, you see, this is more or less, you can't see it because I don't use the, now you can see it's a kind of a sandwich system, and not only the wires are responsible for the use case in the end, also the sandwich. That means we could use for sure a temperature sensor element, which is designed for 1000 degrees, for example, but then there are platinum wires installed, very special classes, and so on. And this is for sure a very, very price intensive design. And this is the reason why we have variabilities concerning the connecting technologies, because sometimes a wire with a silver layer is enough, a copper wire with a silver layer or a nickel wire is enough. And this is the reason why we try to adjust our solutions for your application. And the class system is also regarding the requirements of our customers. That means the temperature levels. The next description is the SMD type. Here you see also how it's created and designed. We have the base plate made of aluminum oxide. We have our meandration. We saw that before. We have the contact pads, which are typically optimized for soldering in that situation, or for gluing. And then we have these metallized caps in the end. We call it caps because they go more or less over the edges, and this is a very good and easy to control connection for soldering. Especially it's optimized for an automatic optical inspection system because of these caps. If you use the flip chip type, which is without these caps, only with contact pads, then the optimized or the automatic optical inspection system is completely different and much more complicated. Keep that in mind. If customer wants to switch from this type to that type, he should at least know that there is an effect in the inspection systematic behind here. And now we come to that quite new technology, that sinter chip. Here we have nothing else than a flip chip version of our historically grown flip chip SMD part, but we add metallization on the backside, which is more or less the preparation for the sintering process. And on top, you have not an optimized metallization for soldering. We have here an optimized metallization for wire bonding. In this situation, aluminum wire bonding is recommended from our side. We come more or less to the end of my presentation. Here we have some exemplary installations highlighted. What you could keep in mind if you are on the customer side and you see what customers try to sense, which application customer has in mind, then we can show you here a PCB type, which could be directly connected on the backside of a plug. This is more or less a charger plug application for the e-mobility world at the moment, very popular, and it's essential to know, especially if you use high power charging, that the temperature is not increasing over a certain point to protect your equipment and also, yeah, the man who is charging his car. That means this is a very simple solution. We saw that in the field that our customers are using a PCB type, press it directly on the backside on the metallic part of that pin, and they fix it with a shrinking tube. You can't see it very good. I think maybe maybe you can see it. It's a shrink tube and it's only pressed on the surface with that shrinking tube. Then we have for sure different other types which are very simple protected, but it's a very effective protection. We take a typical wired type, a M type, for example. We take a version where the wires are prepared for laser welding, because this is a very, very reliable interconnection technology. We laser this M type directly on that cable. Then we protect this system from the environment with a shrinking tube, but this is a very special shrinking tube. This is a shrinking tube with a melting part inside of the shrinking tube. That means this is really very good sealed. And you see here on that cables that melting part of that shrinking tube is also melting the insulation of the cables. That means it gets really very good in contact. That leads to very high forces if you want to destroy the system. That means this is really a good application for harsh environment, and a lot of customers are using these kinds of sensors for e-motors, especially to control the winding, because the winding must be protected for overheating because of magnetic effects, and also because of insulation topics. This is the application, what you see here with that golden shiny PCB for our sinterable SMD, which is called the SC as sinter chip. And the position is here very central between or in the middle of 4 power dies. In that situation, these dies are IGBTs. And the better this power module is working, the higher is the frequency of the switches in that IGBT diodes, or more or less in that IGBT modules, and higher frequency leads to higher temperatures. And this is the reason why we can get very close to these dies to find or to detect the real temperature, or very, very close to the reality, the temperature. And this helps our customers to protect these IGBTs very good for overheating also. It's more or less always the same end application. It's a protection for overheating. Currently we speak with some customers for we call it semi-flexible solutions. We have here a PCB, but a flexible PCB could be PI foil, could be also an epoxy foil. You see there's a circuit on top, and on some positions of these circuits, we can position our SMDs here, and then you could play with that system. This is a version which has also a self-adhesive backside, and you can use it as a sticker, or like a sticker. You can stick it wherever you want. Put in that area kind of a plug system, and you can detect the temperature where this flat cable, I will call it, is sticked on. And yeah, this is a very good responsibility, or the response time is optimized because you have a flat surface here and you can directly contact it to a flat surface. That means the heat transfer is very direct. Yeah. And then we have here a complete different kind of technology. We call it housed sensors or value add sensors. The reason for value add is there is not only the sensor element itself, there is a lot of value add for our customers, what we try to offer here. And the essential message is we are able to support our customers by delivering a protected sensor, not only a sensor element. Yeah, this is more or less the end of my presentation.